From previous work on Newton's laws and kinematics, we now have ways of describing how something will move in the case of constant acceleration, and we now have a way of explaining what causes an acceleration, namely having a net force on a body. There are many ways, of course, of now doing problems where we can apply forces, see how it will accelerate, see what its position will be after time. But we've also, of course, seen that because force is ultimately a vector, as will be acceleration, of course, this can get a bit complicated. We do our free body diagrams, we choose a coordinate system, we have to then apply Newton's laws in multiple dimensions, etc. It can get cumbersome. So we want to come up with another technique of possibly doing problems, and one that might give us the ability to do problems that would otherwise be very difficult in the standard way. So if we were to try combining our information about acceleration from forces and kinematics, we might be able to do something. Now, if we use the current equation, we would have to have some time information, but we have another kinematic equation we could use. The final velocity squared equaling initial velocity squared plus 2a x minus x naught. And remember, this is a one-dimensional kinematic equation. So let's say, for example, we're doing everything in the x direction. So initial and final velocities in the x direction, acceleration in the x direction. And if we then combine that with some of the forces in the x direction, or the net force if you prefer, we'll just call it Fx for simplicity right now, equaling mass times acceleration in the x direction. Well, I could plug in the acceleration from this formula into here, and I would have a direct way of calculating the velocity changes, for example, from a force. So how about I go ahead and do that? I'm going to do a little bit of rearrangement, and so I'll have Vx squared final minus Vx squared initial equals, what will that be, 2 times Fx over m, and then the displacement in the x direction. And I can clean this up a little bit more. I'll move the 2 and inverse m to the other side of this equation, and so I'm going to have the form of 1/2 m Vx squared minus 1/2 m Vx initial squared equals Fx minus x naught. So we now have a very direct way of saying if I apply a constant force over some displacement, I can have this nice direct effect on the change in the velocity and also relate that to what mass of the body I have. And these terms here might also look a bit familiar. We're going to have another way of categorizing this, but we see now if we have some very direct way of just taking force in the x direction multiplied by displacement in the x direction, we can talk about how the velocity will change. So we're going to give a label to these terms of 1/2 mv squared. We're going to call that a form of energy. We're going to call it specifically the kinetic energy, or Ke, because it's basically how much energy there is in this body moving. So in this case then, we can see that if we have some force over the x direction times displacement in the x direction, we're going to basically have kinetic energy at one time minus kinetic energy at another time, or the change in kinetic energy. And we're going to give this a definition as well. We're going to call this the work. So we are going to define work as the change in kinetic energy, and it is caused by having a force in the direction of our displacement. In fact, we can give this actually a bit of a vector form as well. So we're going to introduce some new notation for that. So we're going to have work is force times distance. And in this case, the distance is a displacement vector. It has a direction. Force is a vector. We've been using that before. And when you multiply vectors, it can actually come out in two different ways. You could multiply two vectors and get a scalar quantity, which is what work is going to be here. It'll be a scalar form. Or you could multiply vectors together and actually get another vector. We'll deal with that later when we start talking about torques. But in this case, where we have this, what we call the dot product, what that means is the same as taking the magnitude of force times the magnitude of the displacement multiplied by cosine of the angle between those vectors. So this will, for example, produce that if you're having displacement forward in the x direction, and you have a force pointing in that same direction, you would get a positive acceleration in the x direction, and so you should speed things up. That's exactly what we'll see here, that if force is in the same direction as the displacement, that means that theta is going to equal 0. And in that case, cosine of 0 degrees is 1. And so it'll just be force times distance. On the other hand, if, for example, force is in the opposite direction as displacement, that would, we'd expect to cause an acceleration that would slow something down. And the angle between those two vectors would be 180 degrees. Cosine of 180 degrees is -1, which would imply negative work and a negative change in kinetic energy. Now, having a negative kinetic energy change, well, that would basically say that you're taking out some of the velocity. It's slowing down. So that makes sense. Having a force that is in the opposite direction that you're moving should slow you down. And so that would imply negative kinetic energy. All right. This also implies, though, that if the force is perpendicular to the displacement, well, that's an angle of 90 degrees. And what's cosine of 90 degrees? That happens to be 0. And so in that case, any force that is perpendicular to displacement does 0 work. Now, that already kind of fits with what we had with the theorem I had at the beginning here, showing the force in the x direction causing an acceleration in the x direction. It makes sense then that having a force in the y direction perpendicular to all of that isn't going to change your velocity in the x direction, for example. But this more complete theorem of the work energy theorem we have here, that force times distance cosine theta is equal to the work, will tell us that any force perpendicular to the direction of motion won't change the energy in a system, won't even change the velocity. Or I should say, at least won't change the speed. It might change the direction you're going, and when we get to circular motion, we'll be talking about that. But the kinetic energy will not change.